Today we are going to look at the conservation of momentum. Last time we defined kinetic energy by E equal to 1/2 of m, the mass, times the square of the velocity. Today we're going to look at momentum. And momentum is defined as P equal to m times v. Slightly different from energy. Momentum is a part of the mass. The heavier the mass, the more momentum we have, and also the higher the velocity, the higher the momentum. Now, momentum very often is also referred to by a vector form. Is the mass, and suppose it's for a particle I, will be the mass I times the velocity in the vector form. So what you have here is that the velocity v is actually comprises of vx, and for particle I, vxi in the x direction, also vyi in the y direction, and then also vci in the c direction. So vi would then be a vector of the form of vxi, vyi, and vc of I is a vector. So let's consider now two particles. And in this case here, we have two particles for which we have a mass of m1 and a vector of v1. And also, we have m2 and also a vector of v2 for the two particles. Whereby this is a vector of vx1, vy1, and vc1. This is vx2, vy2, and vc2. So in this case here, we could have a particle m1 and a particle m2, whereby the motion is v1, and the motion here could be v2. All right, so the two particles may collide, or they may not collide, miss each other. Today what we're going to look at is basically the special case whereby the two particles may collide together. Now, what we need to know is basically, you can look at the so-called center of gravity of the two particles, meaning that you are looking at the vector v, which is a scale m1 of v1 vector plus the m2 of the v2 vector divided by m1 plus m2. So if you look at this, you can say basically the combine of these two particles of m1 and m2 actually is a joint mass of m1 plus m2 moving at a, in this case, consider that the velocity of that combined particle would be a velocity v given by a linear combination of the two vectors v1 and v2. So that is like the motion of the center of gravity of these two particles. And so very often it's advantageous to look at the motion of two particles from the reference frame of the center of gravity. Not only the position, but as the position moves, we are talking about basically taking this red point with mass m1 plus m2 and velocity vector v as the zero, the frame of reference of motion. So then what you have is then the velocity within this frame of reference. You would have the m1 would be moving at v1 minus v, and m2 would be moving at v2 minus v. So in that sense, with respect to the frame of reference of the center of gravity, the motion, the v vector actually become 0. So you have relative motion of M1 and M2 with respect to the center of gravity. Now that we have defined what momentum is for each particle, we also have defined basically the total momentum P is the sum of all particles of the constituent Pi momentum. And that is then equivalent to the mass Mi of the P velocity I summing over that. So this is a vector sum of the momentum of the different particles. And we can also say that is equal to, in this case here, the vector V for the sum of the particle multiplied by the sum of the masses, Mi, I, and then this is the sum of the masses of the particle multiplied by the center of gravity, just coming directly from this equation. Now, what we are going to look at is basically there is the conservation of momentum. In this case here, for whatever reference frame of motion you have, the momentum is not going to change unless an external force is acting on this system. Now, you would say this will not change if things are moving and they don't collide with each other, because Newton's first law said that things which are in motion will be continue to move at the same velocity. So in that regard, if there's no collision, obviously these quantities by Newton's first law, things in motion keep in a state of motion, the momentum will not be changed. Now the question then is, if these particles collide with each other, would momentum be still preserved according to the quantity we have in this formula? And the answer to that is, according to Newton's third law, which says that action is equal to reaction. So if you have two particles coming together, colliding, then you have an action of one particle on the other, and a reaction, and this could be force. So what you have is you have an action of force F, then the reaction would be another force F, reaction. These two action and reaction of forces on objects are equal and opposite. So that's according to Newton's third law. So long there's no external force acting on these particles. External force. You can have internal forces as the particles collide with each other. Newton's second law said that F is equal to ma when an external force is applied on some masses within the system, then the mass would accelerate. And in that case, because of an external force acting on these particles, momentum is not conserved because momentum is changed by the external force. Let's not consider that. Let's consider that there's no external force here. And we have an example here whereby everybody knows about this. If I have one bead and then I release the bead here and make it collide, well, you see that you have collisions of these beads for which one would bounce off because one bead would create a bouncing of the other. Or if we can do, in this case here, 3 beads hitting the other two, you will notice that we will have 3 beads bouncing off in the other direction. So what you have is an illustration of the conservation of momentum. Conservation of momentum says that if I have 2 beads with a particular momentum, when they collide with the other 3 beads, I will have 2 other beads moving off in the same direction on the other end. So momentum is conserved, and in the case that the 2 beads would come down here, would stop, and then the 2 other beads would come up, and so on. So it would have, this is a perfectly good illustration of the conservation of momentum.